This call is now being recorded.
Between them. Right, so these are the two aspects of straight lines that we know. The crucial point and why we look at geodesics the way we started looking at is on an arbitrary Riemannian manifold, these are not equivalent, right? So of course, in Euclidean spaces, they describe the same object, but on Riemannian manifolds, they don't coincide, these 2 points. Yeah, so we'll try to generalize the first one. We will end up seeing that occasionally it also satisfies the second one, but there will be examples where it does not satisfy the second property. Yeah? So in that sense, we are looking for analogs of straight lines, but having in mind what properties we are trying to generalize, right? So these are not equivalent. So the point really is, so these are not equivalent on a general. I mean, we'll ignore what this Riemannian manifold is. So these are, this we will see soon enough tomorrow, hopefully. Okay, I'll write it. So it's just so surfaces are examples, right? So surface with an inner product on each tangent space, and such that these tangent spaces vary smoothly with the points. Yeah? So that you can measure lengths and angles and so on, as we see in the case of surfaces, hypersurfaces that we are looking at. So so these are more general objects, and so because they are not equivalent, we generalize the notion of straightness. You will see that these are not unrelated even in a general manifold, but they are not equivalent. So okay, so now so we have the definition, and so at least one thing which is immediate perhaps, and this is a little lemma. So geodesics have constant speed. So how does one prove something like this? So simply just from the definition. So of course, speed is just the norm of the velocity vector, right? So velocity vector field. So you look at, so notice 2 things. So gamma prime t, so the velocity vector field is tangential at every point to the surface. The acceleration is orthogonal to it. So these are the only 2 points that are relevant for us. So this is in t gamma t, gamma tangent space at gamma t, but ortho complement of that for every t. So the second condition, of course, is geodesic, right? So what do? We want to say the length is constant. So we'll check whether the derivative is 0. Curves are defined on intervals, right? So then this is just routine. Your bilinear form, derivative of bilinear form calculation once more. So of course, these instances, they're also symmetric. So this, you could write this as twice velocity vector field paired with the acceleration, and that is 0, right? Because one is tangential, the other is orthogonal to the tangent space. So okay, so that's the little observation to start with. Let's look at some examples now. So let's look at the example which motivated all of this. So you take an n surface which contains a Euclidean straight line. So containing straight line. So this is line segment. So this is gamma t being p plus tv. So t is in some interval I, p is a point, and v is a vector. So why is this a geodesic? So you simply have to differentiate. Yeah. So if you differentiate twice, because it's the velocity vector field is constant, the derivative is trivially zero, and so it is orthogonal to the tangent space. Yeah. So what you do is, of course, write out components again, and the derivative is velocity vector field. You differentiate component wise, and you simply notice this. Yeah? So this is a geodesic. Since the velocity vector field is constant. So the acceleration becomes zero. So the second example. So at the moment we can deal with relatively elementary examples, but that is already very interesting. Yeah? So we look at, once we have a little more information, we can perhaps do an example tomorrow, which come back to this and do an example tomorrow after we get enough ammunition. So this is simply the cylinder sitting inside R3. So what is the function that whose level set this is? So is the defined on all of R3. So this is just x1 squared plus x2 squared minus 1. Notice that this is a cylinder. It's an example which you probably have seen already. So this is nowhere zero on the surface, because not all coordinates can be zero. So the gradient, the vector part of the gradient vector field is just 2x1, 2x2, and 0. And this cannot just be 0, because x1 squared plus x2 squared is 1. So now, so we make a guess as to what geodesics could be on the surface. And so of course the first example suggests that, so these are infinite cylinders. So it suggests that you look at straight lines, so going along the length of the cylinder, so to speak. Yeah. So this is likely to be this has to be one of the geodesics. Is this the only one? So what could happen? So how does the sort of the geometry of the cylinder actually affect this? So you can think of, so what other things can you say? Okay, so you can think of course, orthogonal to these infinite straight lines going along the length of the cylinder. You can think of these circles, but these circles are merely sort of lines winding upon themselves, right? So So one might wonder whether these are also geodesics. And instead of the straight line just going straight up, you might wonder whether it's just winding around the wrapping itself around the cylinder. So that could be a possibility. So these are all in some ways various manifestations of the lines or line segments. And so one imagines that these could be candidates for geodesics. So we make our guess. So the tricky part in all of this always just to say that these are all the geodesics, right? So you may guess some examples like this. I'm saying, okay, here is the straight line, infinite straight line going along the length of the cylinder. So it would be very odd if it's not a geodesic, and so on. So we make a few guesses. The interesting question always is the list that you have guessed complete? Yeah. So that is a separate question, but let's make our guesses first and see where we go from there. So let's consider curves. So to be one stroke, all these examples that I mentioned. So this is parameterizing these circles, and you have no control on the third coordinate, right? So the first and the second coordinates have to lie on a circle, so there's not much room there. So it has to be parameterized in this shape. And on the third coordinate, it's a completely free coordinate, right? The function which defines the cylinder. So you just write out a full line there, right? So after all, a cylinder is got by sort of moving a line around a circle. Yeah? So okay. So when is such a thing a geodesic? So here, of course, A, B, C, D are arbitrary numbers for A, B, C, D in R. Consider these. Now, so we want to see, maybe there are conditions on A, B, C, D which which is enforced in order for these to be geodesics. Let's see. So first, anyway, we want to calculate so in order to check whether something is a geodesic, we have to calculate the acceleration, see somehow that it is orthogonal to the tangent space at every point on the curve. And because we are in the hypersurface situation, right? So our n surface is always sitting in Rn plus 1. So one way to do that, and that's what we will do here, is if it is, and because these surfaces arise as regular values, so these are regular hypersurfaces. So we may wonder, one way to say whether these are geodesics is to see whether there's a relation between the acceleration and the the gradient vector field, right? So that is an immediate suggestion in these examples. Yeah. So in any case, we have to calculate the acceleration. So let's first calculate the velocity vector field. Okay, so this is all component wise. Maybe I'll write the definition once. So it's not done. So you ignore the point. So at every point we are interested in. So this is minus a sine at plus b minus a cos at plus b and c. So when you write out the acceleration, of course, the component displaying the line vanishes. So gamma double prime double dot at t. So this becomes gamma t, and so minus a squared cos at plus b. Again minus a squared sine at plus b and 0. So on the other hand, so we want to say this is orthogonal to the, so if this is to be a geodesic, we want this to be orthogonal to the tangent space, to the surface. And so let's calculate the gradient. As I said, that's one, we know the gradient vector field is orthogonal. So we calculate this out. So let me maybe once write the definition again, in case it's a long while since you have, so this is df by dx1 at the point gamma t. So df by dx2 at the point gamma t, df by dx3 at the point gamma t. Right? So easy enough. So we calculate this. So this is gamma t. So 2 cos at plus b, 2 sine at plus b, and 0. Because the curve has so now just calculate the, so you don't even have to calculate normalized by the length, and but this is easy enough to calculate. So in this instance, so let's just write it out. So this is 2. Yeah, sine square cos square, that sort of goes off and you take the square root. So your normal field here along the curve is by its norm. So what is this? So that 2 factor, okay, but that is just cancelling this out. So this is just gamma t cos at plus b sine at plus b 0, but that is a square, because in the I can sort of pull out from the vectorial part, the a squared is common to both the first and second coordinates, 0 and the third, so we can pull that out. So this is simply like gamma double dot t. No, it's the other way, no? So this, so I put an a square on the other side. Yeah, so sorry. So this is, it's okay. So that is the acceleration vector field is a square times the normal. Okay, so plus minus here because orientation. So we don't have to make a choice of orientation. So I put a plus minus there, and so this is so this implies that it is a geodesic. So gamma t is a geodesic, and interestingly, notice that no conditions whatsoever were imposed on A, B, C, D. So this is a geodesic, because that you might expect. Yeah? So sometimes, so additional conditions are imposed. So it's a geodesic for all values of A, B, C, D. On the surface, on the cylinder. So we make a few distinct cases out of this. So what happens if A is 0, right? So you look at your curve again. So if your A is 0, the you're fixing a level for the circle, and then just moving off on the line. So there's not. So this is really the line on the cylinder, right? Through this point, whatever. So cos b sine b, that gives you a point on the cylinder, on circle at some height. So this is a line on the cylinder through which is one of these circles that so the horizontal cross sections, and then you go off on the line. Yeah, so the other extreme case is what happens if you put C is 0, then the line itself is vanished. So you are fixing a certain height here, D, and you're looking at the circle at height D. Yeah, so this is a horizontal circle at height D. So the other point then is when neither is 0. So then you can see that this would be the instance where the line actually winds around the circle. So helix. Yeah. So this was a helical curve. I mean, just a helix would have done, I suppose. So there's a nice picture, which again I didn't have to draw, thankfully. So all we are saying is these examples are geodesics, right? So the vertical straight line, the horizontal circle, and the instance where the line wraps itself around the circle. Yeah, so around the cylinder. So these are the so okay. So let's take another example. Perhaps this should have come first. Not that it's but so this is the circle two-dimensional sphere, sorry, the two-dimensional sphere in R3. So S is so this is of course the two sphere. So the function and so on, So again, notice that the gradient vector field is not nowhere 0 on the on S for pretty much the same reasons as above. Now here we try to make guesses, right? So are there distinguished curves which lie on the surface of the sphere? So you could let's say start with antipodal points. There are very special cases. So you take antipodal points, then of course there is a great circle going through these 2 points. Let's say the North Pole and the South Pole. So what is it called? The latitude, perhaps? No, was it the longitude? Yes, the longitude. So so this goes through the North and the South Poles, and so you could take, of course, these curves to be just semicircular arcs going one way. You don't have to look the other way. You could, of course, as well do that. On the other hand, if the points are not antipodal, what are the possibilities, right? So let me maybe at least one picture which I can try drawing with help. So if I do have something like the equator here, that went out. But okay, we'll pretend that it's not gone out of the circle of the sphere. So these, the case of antipodal points. So okay, I didn't put the north and the south poles as I said, but okay. So this is some point P, another point which we pretend lies on the sphere, the picture. On the other hand, of course, you could take points, just points like this, right? So P prime and Q prime. So now notice that if you take any 2 distinct points here, you of course so maybe I draw this better. So if I erase this, oh, the shading is gone, but that's okay. Let's see. So even on this, right? So I could, instead of taking them on the, maybe the easiest thing is to just draw 2 points here. So let's call them A and B. So they are not antipodal. Of course, they still lie on some great circle here, right? So given 2 points, because what are these 2 points on the? So we might actually consider, there are two curves to be considered here. One is this black shaded part. The other, of course, it's between A and B. I can go the other way, the red dotted one. So these two. So in the case of antipodal points, they are the same, but they're meaning they take the same shape. Here, they don't. So these are, of course, possibilities for distinguished curves on the surface circle of the spheres, and so we might want to make a guess that they are candidates for geodesics. We'll see that they are indeed. So the general idea is you take two. Let me state it this way. So you take two distinct points on the sphere. So this A and B, they could be P and Q, but take two distinct points. Now these are of course linearly independent unit vectors. Yeah. So now consider W to be the unit vector. Maybe I put an arrow on top everywhere. So W, so the unit vector. So distinct points, so they are linearly independent. Yeah. So and normalized. So unit vectors. So because they lie on the sphere. So in the direction of the cross product, which one? U cross V, that thing cross U. So then where does W lie? So U and W actually form an orthonormal basis for the plane determined by U and V, right? So our choices make that. So U and W, O and B for span of, so the plane determined by U and V. Maybe I should write that better. Yeah. So for the plane so the great circle passing through U and V, now you can parameterize as, so of course the great circle is just a circle got by getting a cross section of the sphere by a plane which contains a diameter, right? So you imagine what it is, but how do you make that precise? You say you take a plane, you look at the cross section the plane makes on the sphere, and if it is such that the diameter actually lies in this cross section, then the circle which you get by the intersection is a great circle. Yeah? So this then gives us that the great circle passing through these. So is parameterized by cos cos t and sin t. Of course, I mean already. So in all these examples, you have to rule out the these are the non-constant geodesics, right? So the constant curve is always a geodesic. Yeah. So the velocity vector field itself is 0. So and so is the acceleration. Yeah. So these are, we are only looking at the non-constant ones. So this is cos plus sine. So cos, I could throw in a parameter here. Because everything is normalized, this is probably just 1 suitably. Sine 80 and 0. Because with respect to those, you write as sum of this and that, right? So u plus v, cos 80 times u, sin 80 times v. And so when you write as coordinates with respect to this basis, this is what you get. So now let's look at the velocity vector field. So once you have a candidate, then it's straightforward verification, right? So so you just write this out. So this is gamma t, and then minus a sine 80 minus so a is cos 80. So in some ways, this whole calculation is subsumed by the earlier one, right? So here you have fixed a height on the cylinder, so that's sort of calculation. Yeah. So and so the acceleration. So this is vector field is gamma t. So a squared cos 80 a squared, no, again minus everywhere, sorry, minus sine 80 0. So this is again, so plus minus a squared. The calculation for the normal is pretty much the same. Yeah. So the third coordinate isn't there. So in the previous one, here it is, but the curve, on the curve it is 0. So it, so on the surface it is there, but on the curve it isn't. So so I will repeat the calculation. So these, so what is the upshot? So the moral really is that great circles or segments of great circles, perhaps. Yeah. So great circles are geodesics. Because there's nothing particular about S2 in this example, right? So you could very much do the exactly the same sort of calculation. So maybe not what are the geodesics. So or in other words, calculation above, hold for, or similar calculation. So high dimensional spheres. So what we did so far is just to say, okay, so we've given a nice enough surface, an explicit function, which is just, in this case, homogeneous polynomials, as easy as that. And we are able to make some guesses as to what could be geodesics. They turned out to be geodesics. Now, in order to answer whether these are all the geodesics or could there be some other, we need the fundamental result about geodesics, and that is as follows. So this theorem really tells us that you take, I'll state it just for surfaces. So on an n surface, I fix a point and a vector in the tangent space of the point. Then there is a geodesic, unique geodesic, going through this point and having this vector as the velocity vector at the initial point. Yeah. So, and of course, again, you can extend it to a maximal, just as we like we did for integral curves. We can get a maximal geodesic by patching together local ones. So that involves that a similar result. Yeah. So let me state this explicitly. So S is an n surface in Rn plus 1. So fix for, so given P in S and a V in Tp of S, there exists an open interval I containing 0 and the unique geodesic so gamma from I to S such that it passes through, what are the requirements? It passes through the given point and has the velocity vector at that point to be the given vector. So yeah, this is just the associated function and its derivative. So the then a statement about maximality. So the second point is just an addendum. So the first one really tells you that there is a unique, so given a point and a direction, because a point on the tangent vector you should think of as a direction, right? You imagine something like a sphere or a surface and look at a tangent plane somewhere on some at some point. So any tangent vector is giving you a direction at that point, right, in the tangent space. So given a point and the direction, you have a unique geodesic. Did I write unique? Yeah. So and then there's a statement about maximality. So if you have another curve which is geodesic, so if is another geodesic, then I mean geodesic with the same initial conditions, right? So with passing through the point P and with the initial velocity as V. So then we have a maximal one. And these two coincide there. So eta equal to gamma restricted to I tilde. So such a geodesic is called a maximal geodesic. In S, or maybe unique. So it's called in S through the point P and having the initial velocity V. Okay, so I only briefly indicate what happens to the proof. So as you may imagine, this becomes a question about ODE. So the essential part always in this is, so so your surface is regular hypersurface. Yeah? So this is for some C in R. and some f defined on some open set in Rn plus 1. So this is a smooth function. U is open. Containing, so you, by definition, you containing S, with the additional point that on the surface itself, the gradient is non-vanishing. It all this part of the package of surface and surfaces. Yeah, so now that the gradient, so the function is smooth and the gradient is non-zero on S, so it is non-zero in some open set containing S, right? So we could, without loss of generality, take U to be this. You could shrink neighborhoods to do this. Yeah. So if needed, so in some open open set, subset U, no, U was already there, so okay, it's okay to give the same. I don't give a name here, so some open subset of Rn plus 1, and by shrinking if necessary, you assume this to be U. Going to a smaller neighborhood of S. To be U, on which the function is defined. Now write as you would do. So on S, this would give, but this you write on U. Because on S itself, this will give you a normal vector. So now we want to, so we are given these initial conditions, we want a unique geodesic. So let's see. So gamma is a geodesic if and only if the acceleration vector field is orthogonal to the surface at every point of the curve, and this is the same as saying that, so calculation that we used already once yesterday. So this is some, you get a function that relates the scaling function, so to speak, at every point you get some value, so you get a function overall as you vary t. So it's proportional, yeah. So the acceleration is proportional to the, so where here g is a smooth function from I to R. This is smooth. Now this is, of course, if and only if, again a trick we used yesterday, we get G by taking inner products. So this is then, so if maybe I write it as I did yesterday. So G of t is actually given by pairing the normal with the for all t. So removing all these t's, so maybe I write it, so G is gamma double prime n composed with gamma at that pairing. But now you notice that now we use the derivative along the curve that we had. So, and the properties that it displayed. So you take the velocity vector field, you pair that with the with n along the curve, look at its derivative. So this is smooth function, this derivative. So what is this? So by the properties of these derivative along the curve, we know that this is that plus the derivative of the normal along the curve. Now this is 0. Yeah. So this is why we plug this in. So this implies that your because the normal is the velocity vector field is tangential, the normal is normal, is orthogonal to that, and so this gives us that the acceleration paired with the normal vector field, which was our g, by the way. So this is actually minus the velocity vector field paired with the derivative of this along the curve. Yeah? So the dot. Sorry. So with that calculation in mind, so we can say with the go back to the if and only if conditions that we had. So this is if and only if g is actually is equal to minus of so now you plug the whole thing in the initial equation that we had. So gamma is a geodesic. So what is the upshot here? So in terms of velocity vector field and n, we get that gamma is a geodesic if and only if. So the velocity vector field, you substitute for g in this formula here, the one which I'm boxing. And so there is a minus which comes to the side. So you get gamma prime. So I'll remove all the t's. So the acceleration plus velocity vector field paired with the derivative of the normal along gamma times the velocity times the normal vector field. This is 0. So this is a second order system of ODEs. Yeah. So all that was just to say. So these are called the geodesic equations. So this is called the geodesic equation. And so something, so curve is a geodesic if and only if it satisfies the system of equations. And so what is this? So this is the second order derivative that is there. So it's a system, again, components, right? So we have an n plus 1 components for each of these. So the system of second order ODEs. Now second order ODEs, so you have two initial conditions, one condition on the function and the other on the derivative with initial condition. So initial condition on gamma. So that is where it passes through. You fix that point. So this on the function here. So that is, and another one on the derivative. On the velocity vector. So that is gamma 0 is v. So V, of course, is something in the tangent space at P. So this is T gamma 0 to the hypersurface. Now simply a matter of existence uniqueness. So invoke differential equations again. Of solutions for such systems. Again, use uniqueness to patch up local ones. So what we use is show that if you have geodesics gamma and eta, with the velocity vectors coinciding for on some point in the intersection of the domains. There's always an intersection for the domains for us because all curves we consider in neighborhoods of 0. So for some t naught in the intersection of the domains, then gamma is equal to eta on this intersection. So you can patch all of this, get a maximal one, right? So it's very much in spirit as. However, so the whole point here, and so I is so all of this is is not enough, right? So you may say, okay, so we're all done. No, but what is to be shown that a solution for this equation actually lies on the surface, right? So as we did before, so you have to show that f of gamma for every f of gamma t for every t is c. Yeah, so you have to actually say, because all these calculations is these are done in some open neighborhood of the surface, right? So and the system is solved there and so on. However, you have to then see that this forces the situation where the curve actually lies entirely on S. Yeah, so show that.